Consuming iBus signals with an Arduino. Today on Mikey's Lab. Welcome back to the lab. Today we are going to be looking at consuming the iBus signals coming out of an A8S receiver for the FlySky protocol. So lab code up. We're going to learn something today. If you haven't already, go ahead and hit that subscribe button down below to ensure that you get all the latest updates on science, engineering, making, DIY that we put together for you every single week. Now, consuming an iBus signal is not necessarily difficult, but I couldn't find a lot of resources out there. So fair warning, my solution is based heavily off of the multi-wheeze implementation for iBus. I have made some what I would consider to be improvements to the source code for it, but we'll go over all that in a moment. So what we need to start working on this project is simple. We need the receiver for the FlySky. We need an Arduino. We need the FTDI cable in order to program the Arduino. We need 4 LEDs, a breadboard hooked into my main bench power supply for 5 volts, and some jumper wires. So the first thing we're going to do, I know that I have the direction pins in the software set to pins 7 and 8. So we're going to go ahead and connect these jumper wires here. And we're going to connect them over here as well. And then we are going to... Now normally when you're using LEDs, you'd want a current limiting resistor. This is a temporary setup, so I'm going to risk the ½ cent LEDs. So what these LEDs are going to do for us is these two are going to indicate the direction that the motor controller is being told to spin the motors. The next jumper wires we're going to use are going to go to pins 5 and 6, which were chosen because they have a very specific PWM capability, timing-wise, that will make controlling motors much easier. So once again, we're going to take the LEDs, and we're going to go from that signal pin to ground, and this signal pin to ground. Okay. The last thing we need for this particular example is the receiver itself, which we are going to plug into RXI, ground and positive, if my fingers will remember how to work. There is one trap for new players, or one caveat when dealing with this particular module, and that's that soft serial, which was my first instinct to use to receive the signal from the receiver. That's a weird statement. Anyway, to receive the signal from the receiver is too slow. I also originally, when I was going to debug, was going to use an OLED display in order to show the position. That slowed the code down too much as well. So we have to use a physical serial port with the Arduino to get this to work. Now that means that every time we want to flash a new program to the Arduino, we must disconnect the receiver from the Arduino. Otherwise, it will fail to flash every time. It'll get frustrating. You won't be sure why. And it's because data is being sent from the receiver and it's going back to your PC, and it's confusing the program that's trying to flash. So every time you want to update the program on this particular experiment, we need to unplug the receiver. Just like this. And then you'll be able to flash perfectly. Okay, so let's go ahead and power this up. Okay, so apparently I did not screw anything up. I just forgot that I set an arm switch on the transmitter. Now you can see, I believe you can see anyway, I'll know when I go to edit. We have the two LEDs that are currently at maximum brightness. This one and this one. indicating that they're both at full speed. If we go closer to center, the motors slow down, and then our direction flips, and we start to get more intense on the LEDs, indicating the speed is going up. And as we turn, one side slows down and eventually changes directions. The other side slows down and eventually changes direction. Now, when we look at the code for this Arduino and we look at this, I'm going to be upfront right now. The steering code is something I still need to work on. It's a form of channel mixing since we use differential drive on this particular rover. I don't like the math yet. I will probably do an entire video on the finalizing of that once we get the full I2C control of the rover as well. So with that said, let's dive down and take a look at the code. Alright, so here we are at my PC. We're looking at the code for the drive controller. As I stated before, my code is heavily inspired by the multi-Wii implementation of receiving iBus signals for this particular device. I believe that it was a decent implementation. There's still some areas that I feel I greatly improved upon. Let me know in the comments down below if you think I'm out to lunch. So the first thing that we do is we set up a couple of defines. The first define is the buffer size for an iBus packet. Now I left a comment here because an iBus packet has a 2-byte header, up to 14 channels that are 2 bytes each, and a 2-byte checksum. So what this means is that you're going to have a 32-byte packet every time the receiver wants to send an update back to the Arduino. So we know that we shouldn't act upon anything until we've reached the iBus buffer size. Otherwise we won't have complete information and the values could be completely corrupt. iBus max channels is set to 10, however, as you can see here. I know I just said that it has up to 14, but my transmitter can only support 10, so that's what I went with. The next couple of defines here are the channels as they map to the transmitter itself. So throttle, according to the source code, is channel 2, which is here, going up and down on the non-ratcheting input. What that means is if I move the stick to the left or the right, it snaps back into place. But up and down, it stays whether you let go or not. So the rudder channel is channel 3, and it moves back and forth on the same stick. The last channel I set is for arming and disarming the control of the rover. What this will tell the drive controller is ignore the Raspberry Pi, I'm taking control. That way if the autonomous functions start to malfunction while we're prototyping, we have a way of taking control of our rover. Now as you can see, I've defined that as channel 4 and called it ARM channel. When we set up the breadboard, you'll notice that we put in 4 LEDs to 4 pins. These will line up with these. So the left PWM pin, which is the speed that we're telling the motor controller to run the motors at, is pin 5. The right channel for the right motors that we're telling how fast to spin at is channel 6. The directions and the direction pins, self-explanatory. If they're high, they move in one direction. If they're low, they move in another, so they're not PWM'd. And then we have an LED 13 to tell us whether or not the rover is currently in manual control mode. We set a couple of integers up here in order to process through the signal itself. iBus index indicates where we are in this particular iBus packet. Right? An array of the buffer size so that we can have a single iBus packet into this particular array of integers. And then the RC value is going to be an integer array, max channels that the transmitter can send, that contains a value of 1,000 to 2,000 per channel. This will allow us to know the position of the sticks when we're receiving the data. For global control, we also have an RX frame done. I set this up because I was having a lot of problems with somehow an update being halfway done before I go to read it. I'm honestly, at this point, I am still not sure how on an Arduino we wound up with a race condition, but somehow we did, and this solves it. So we have the two throttles. This is a current running tab of where we are for each of them. So we have the throttle left being an integer, the throttle right being an integer, and the direction, the current direction being an integer as well. Alright, so that's pretty much the global part of the configuration for this. We enter into the setup. We begin serial at 115200. This is very important because that's the set baud rate of the receiver device itself. So we can't go slower than that. We can't change it. There's no auto sensing on this receiver. So it's going to talk at 115200. So that's what we need to listen at. That's also why soft serial will not work for this solution. We set up the pin modes. All of them become outputs that we defined up above. We turn off the manual LED pin just in case pin 13 comes on in a high state. And we tell the serial line, because we can still send to a serial line since it's not connected to the receiver. We tell the serial logging that the setup is now done. Okay, so now we enter into the main loop of the program itself. First thing we do in the main loop is we read from the receiver. So if we go down to the function to read from the receiver, as soon as we start receiving on the receiver, we set that the frame done is not true. This will allow us to, as we continue to go through and get pieces of data, wait until the data is pure before we act on it. So when we get to that point, we look to see if there's serial data available on the serial bus. If there is, we read it into a variable called val, and we start looking for the header of an iBus packet. Now, because these can come up at different times, they can start paying attention at different times, we don't want to do anything with the data we're receiving until we have received what we know to be the first packet. And a header on an iBus packet is 0x2040. So we look for, are we at iBus signals, iBus index 0, which means it's the first part of the packet. If we are, is the value 020. If that's true, then we continue with where we were and we verify that we're at 0, we return and we wait till the next byte comes in and we read again. When we read again, are we at iBus index 1? If we are and the value is 040, that means that we've consumed the full header at this point, so we know we can continue. If we have not, if we're at index 1 and it's not 0x40, we know we have to start over, okay, and hope that the next packet is the beginning of the header of it. If not, we just continue till we find the beginning of the header. So we set iBus index back to 0, which puts us back to the beginning of the array, and we return from this function, and the next time we read, we'll check again. Assuming that we do have a valid header, or we're not looking for the header at this point, if we are at iBus index of greater than 1, we're no longer looking for the header. Right, we look to see, are we at the end of the buffer size? Do we want to stop reading at this point and update all of our channels? If we are at the end of the buffer size, so if we've hit the 32 bytes that this buffer is, we set the iBus index back to 0 so that when we're done this, we go back to the main loop of the program and we start looking for the header again and find our next packet window. So at this point, we're in this loop here, indicating that we have the complete packet. Okay, we set iBus index 0 so that the next time we run through this read Rx, we know that we're looking for the beginning of the packet again, and if we miss it, then we just wait for the next one to show up. We currently are looking at which byte, these two integers here store which byte we're looking at for the actual RC value. And then we go through a for loop for the max number of channels for the transmitter. So in our case, we've set this to 10 up above. So what we do is we set RC value I, right, equal to iBus, the high byte as defined by this integer here, shifted left 8 bits, plus the byte below that. So this would be the third byte, shifted left 8, plus the value of the second byte. Now for debugging purposes, I also have it printing that to the serial port. with this base. Then we change high to be 2 bytes higher and low to be 2 bytes higher. This causes, well, I guess a value of 2 higher. This causes the values to leapfrog as you go through. Once we're done printing the values for all of the channels, we do a serial print line to feed a new line, and we say that the RX frame is done. And we return. So in the event that we were not done completely reading the packet, we set the iBus value at iBus index, whichever byte we were reading at the time, to the value that we have read. We indicate, or we increment iBus index, and we return. So the next thing in the loop that we do after we've read the serial coming in is to check to see if the frame is done now. If the frame is not done now, then we do nothing. Right? We loop back and we start read RX again, and we continue to do this until the frame is actually done. If the frame is done, we look at the RC value of the ARM channel we defined, which, if you remember, is the middle switch on my transmitter, to see if we are currently in manual control. Because if we're not, we don't care about the values we just read. Right? If we are, then we care about the values we just read. If we're armed, we set the digital pin to indicate that we are armed and we are in manual control. And we call a function called update motors. So update motors is where I still have a bunch of work to do. So we're not going to talk about it a whole lot. All of this does is it sets the speed and direction of each motor based on the values of the channels from the transmitter. This is likely to change a lot, so I'm not going to go into a whole lot of detail here. You're welcome to take a screenshot or take a look at the source code after, and give me any feedback you might think I need. I am aware that with this calculation here, that unless the rover is turning, no motor will ever be run at 100%. The max it would ever be run at is 50%. I did that on purpose. That is to extend the life of the motors. The motors are rated for 12 volts, and if all I ever feed them is 6, they're going to last a lot longer. I'm not too concerned with speed. We're not trying to build a radio controlled car here. I want it to operate, and I want it to be resilient. So I did that on purpose. So then we come back up here, and if we're not in manual control at this point, right, we fall into this else condition. We set the manual pin low to turn it off, to turn the manual LED off. We reset the throttle to neutral for both channels. We write that to the PWM pin to stop the rover from moving, and we set both direction pins back to forward, which is our default condition. This here will eventually be a switch case, or a select case, depending on which language you primarily use, in order to control this a little cleaner. Right now it works fine. So what we're going to do now is we're going to take the circuit that we have with this particular program. I'm going to upload this program to our Arduino, unhooking the receiver first. Okay, so if you give me a second now, I'm going to get the rest of this test bench set up, and I'm going to show you this code actually working with the motors. Okay, so for this part, I just want to show this control unit working. So what I've done, if you dive down to the bench here, I got one of my test motors, which just has the XT60 connector attached to it. I have our motor controller that we are going to be using for the rover itself. I have a 3-cell LiPo battery, right, and I have the circuit that we just built up. So if you take a look at the motor controller, you can see that this one requires a ground, a 5-volt, PWM for motor 2, direction for motor 2, PWM for motor 1, and direction for motor 1. So what we're going to do is we're going to take a bunch of these wires. I'm going to use orange and green for power, because that just makes sense to me. So we're going to go to ground, 5 volts here. Orange will be 5 volts. shut off the power to the device while I do this. Ground will be green. Okay. And now we're going to go with the PWM for channel 2, which is this black wire here. And we're going to tap in between the other jumper and the LED. And grab a blue wire for this one. And this is the direction for that motor. Alright, which is going to be, oh wait. Yeah, motor 2, okay. So motor 2 direction is going to be this guy right here. So again, we'll tap in between there. PWM for motor 1. Tap on the other side. And the last wire is always a pain in the ass in this controller. I don't know if it's the pin header on the controller or my wires, but it's always a little hard to get into. And that goes to the direction pin and we'll tap into there. Okay? So the next thing we're going to do, we're going to take one of our motor leads that would normally go to the leg of the rover, and we're going to plug it in like that, attaching the motor to it. We are going to take our LiPo battery. We are going to plug our LiPo battery into our motor controller, like so. We're going to re-energize our circuit. Energetic little guy. Okay, so as you can see, we have our test motor connected to our circuit, which is connected to our motor controller. And as we raise the throttle, the motor starts to spin. So there we have it. The basics of the motor controller itself, we obviously are going to burn this to a different Arduino. And we are going to connect it in place and attach it to the rover as soon as we have the waterproof enclosure for all of this. So I hope you learned something today. Thank you for joining me in the lab. If you haven't already, click that subscribe button down below and smash that like button if you like this video. If you don't, tell me why in the comments. Once again, thank you for joining me in the lab, and I will see you next time.